Okay, good evening, everyone. So we're in week 8. Actually, scratch that. I'm not entirely sure what week we're in. It's kind of chaotic right now, but this should help you go through and understand what exactly we need to talk about. Today, we are going to discuss unit analysis. Now, units are important because they kind of form the basis of mathematics and numbers as we deal with them in the real world. So if we look here, right, we can see that numbers don't really have meaning by themselves. They need this thing units to be able to get their meaning. And basically what units do is they tell us what we are counting or measuring. So for example, if we had a number of horses, right, we could just say there are 12, but if we just said there are 12, right, we just said there are 12, it wouldn't really have much meaning until we put the unit on there, and then it tells us what there are 12 of. So there are 12 horses, right? The horses is the unit, right? That's what the unit is. So if you look around you or just go around in your daily life, you'll see that all the time you're counting things, right? So if you say I have $100, the unit is dollars, right? If you say I have 3 kids, the unit is kids, right? So we can see the units really by themselves don't give us anything. They don't give us any numbers by themselves. I'm sorry. Don't give us anything. We need the units attached to it to get meaning from the numbers, right? So if we don't have units, what we end up having is chaos and confusion. We don't want that. So anytime we say a number, we want to attach the unit to it. And that's a habit that you should really get into. Anytime you say a number, attach the unit. Say, what are we counting here? What are we measuring here? When we work with numbers and units, right, we don't just do the operations with the numbers. We also do all of the operations with the units, right? So for example, if we had 6 horses, and then let's say somebody came over and gave us 3 more horses, we would say 6 horses plus 3 horses, right? That would equal what? It wouldn't equal 9. It would equal 9 horses, right? Now, the reason why the unit didn't change is because units have special rules when we do operations on them, right? When we add units, if the units are the same, that's key. If the units are the same, when we add or subtract them, then we don't actually change the unit, right? That's why when we get 6 horses plus 3 horses, we got 9 horses, right? You can think of it with money. If you add $5 plus $8, what do you have? You have $13. But on the other hand, if we were to multiply or divide quantities or numbers with the units, then our units can do one of 2 things. Either they can cancel each other out, or they can create new units, right? So that's multiplying or dividing numbers with units. Either they cancel or they create new units. And we'll look at how that works exactly in a little bit. Moving on, let's look at a couple of examples. Right? So let's say we had 3 apples, right? And we got 5 new apples. How many apples would we have? Well, we know it's apples because we just had 3 apples and 5 apples. So what do we end up with? We end up with 8 apples. Now, this seems really simple, but this is kind of really foundational. And understanding this will take you far as we start doing more complicated examples. Let's do an example with multiplication, right? Let's say we had a shape. Let's just do a square. And, well, it's kind of not really a square. Let's say this is a rectangle. And let's say the dimensions were 5 inches by 6 inches, right? How will we find the area right? So we know area equals length times width, right? Length times width. So to find the area here, what we need to do? The length, which is what? 5 inches, right? Times the width, which is what? 6 inches. And when we do that, what do we say happens when we multiply or divide units? Either they cancel or they create new units. So what we end up with, right, in this example, sorry about this distraction. What we end up with is when we can multiply the numbers, 5 times 6. What do we get when we do 5 times 6? We get 30. Now we need to do inches times inches. When we do inches times inches, what do we end up with? Well, if we multiply two numbers and we add the same number, we multiply it by itself, right? That's the same as squaring the number. So when we multiply inches times inches, we get inches squared. So the area of this rectangle is 30 inches squared. So you've seen that. You've seen feet squared, or another way of saying inches squared would be saying square inches. That's something that you may see, or you may see just like IN squared. And it's the same concept, right? We could do the same concept with a three-sided shape where we had three things and we would define the volume, and we would do, let's just actually draw it out and do the example. Let's say we had a cube. If we had a cube and let's say the length was 3 feet, that little line there means feet. The width was 2 feet, and the height was 5 feet, right? In this case, we would need to do, to find the volume of this cube, right? We would do length times width times height. And when we do length times width times height, what do we multiply? Well, we have 3 feet, right, which is our length, times 2 feet, which is our width, times 5 feet, which is our height. Now we can do the exact same thing, multiplying the numbers. 3 times 2 is 6. 6 times 5 is what? Well, we got 30 again. I should have probably used a different number. But we get 30 again. Now we need to multiply the units times each other. And it's just like we did when we had the inches, right? Feet times feet times feet. When we multiply a foot times a foot times a foot, we get feet cubed, right? Because there are 3 of them, and we multiply something by itself 3 times, we're cubing it. So we get 30 feet cubed, right? And another way you'll see this is cubic feet, right? Or you'll just see feet cubed. So this is an example where multiplying units, right, gives us a new unit. So here we multiplied feet times feet times feet. What do we get? Cubic feet, or feet cubed. We multiplied inch times inch, inches times inches, and what do we get? We got square inches, or inches squared. We can do the same thing with division, right? So let's say we have an example where, there we go. Let's say we had an example where we were trying to figure out how fast we were traveling. And when we did it, we saw that we moved, let's say we moved 30 miles, right, per every 1 hour. So in this case, what we'd be doing is every hour, right, we move 30 miles. So here, what we would have is miles per hour. So this would give us something like this, where we have 30 miles. Now, per means division. There are a couple of words that gives you clues as to what operation to do. Per is one of them, means division. So we have 30 miles per 1 hour. Now, you've heard it before. You've heard that unit before, right? Where we're dividing miles by hours. When we do 30 divided by 1, we just get 30. It doesn't change, right? But when we do miles divided by hour, what do we end up with? We end up with miles per hour. So our unit here is miles per, I don't know what kind of weird H I wrote there. Miles per hour, right? Or MPH, which is a unit we got by doing division. We'll look at units canceling out in a second, but this is just the basic thing of how we're working with units. Notice how when we did all of this, we worked with the units and we worked with the numbers themselves, right? We worked with the units and the numbers. So here we worked with the apples, right? And we worked with the number. Here we worked with the inches, right? And we worked with the number. We ended up with this new unit here. Here we worked with feet, right? Feet. And we worked with the number, and we ended up with this new unit here. And here we worked with the numbers, right? And unit to end up with this new unit here. So we can do a lot with units, and units are really where we start to see how numbers can be important kind of in the real world. Because in the real world, we never work with numbers by themselves. Because again, numbers do not have meaning if we don't attach units. So numbers, right, and this is what I want you to remember. Numbers have no meaning without units. Numbers have no meaning without units. Okay? Units are critical in math. And every time we write a number from now on, I want you to include the unit in there. So moving on, remember I said that they're keywords that can kind of give us a clue as to what operation we're expected to do. So one of those words is per. And every time we see the word per, we need to think that we need to do some kind of division. And we already did this example where we said miles divided by hours, right? We say miles per hour, right? Another word that kind of gives us a clue is anytime we see of or hyphen. If we see a hyphen, by a hyphen we just mean dash. That's what we mean, a dash like that. And whenever we see something like that, we want to think that we need to do multiplication, right? That's what we need to do. We need to do multiplication, right? And an example of that would be kilowatts times hours, where kilowatts, right, that measures, as a measurement of energy, but a lot of times we think of it as like measuring electricity, right? So kilowatt times hours, we end up with this new unit where we say kilowatt hours, right? Notice the hyphen. See the hyphen there? That means multiplication. So kilowatt hours. And when we did the percentages, you already saw that of always means to multiply. So anytime we see of, we need to multiply. We talked about this example just a second ago. We talked about this word just a second ago. And this word was square. So when we see square, it's just like when we're dealing with numbers by themselves. That's raising something to the second power. So feet times feet, we get feet squared. And we can read that as square feet or feet squared. Same thing when we see cubed, right? So when we see cubed, we want to do the exact same thing. So if we see cube or cubic, right, we're raising something to the third power. So if we see feet times feet times feet, we can say feet cubed, right? So cubic feet or feet cubed. So just some other ways we can get a clue on what we need to do when we see certain words, how to give us clues. Now, when we talk about unit analysis, right? What we're talking about is manipulating units where basically you want to change the way that we count something or the way that we measure something, right? So for example, let's say we don't want to count something. Let me think of an example. So yeah, again, it's just changing the way we count something or the way we measure something. So let's say we are trying to, an example is kind of like what we already did. So what we already did was we looked at the shape here, right? And we were looking at a rectangle, and it had a length. So here our length would be 8 inches. Here our length will be, say, 5 inches. And what we're trying to do is, instead of just seeing the inches and inches, right? Let's say we want to instead write the area. So an area is measured in something being squared, square inches if we're dealing with inches. So we want to do the 8 inches times the 8 inches, 8 inches times the 5 inches, right, to get 40 inches, right, squared. Let me just write that a little neater. We get 40 inches squared. Okay, another example might be, let's say we were having a party, right? And for our party, I'm going to erase this example really quickly. Let's say for our party, we wanted to buy some soda for our party. Now, our party, we know that we are going to have 15, right, guests at our party. So we're going to have 15 guests. And we also know that each guest, right, is going to require, so let's say we have each guest will drink, let's say each guest will drink 12 ounces of soda. So that's just like 1 can of soda. So each guest will drink 12 ounces of soda. Now, right now, we are counting how many guests will come to our party, right? We're counting how many people we'll have to our party, at our party, in guests, right? So we're saying there are 15 guests. But what we really need to know, we really need to count how many people we'll have at our party, not in guests, but in soda, because we're trying to buy soda. We can't go to the store and say, oh, I need 15 guests worth of soda. We have to go to the store and say exactly how much soda we're going to need. So we need to count the number of guests, right? Not in guests, but in soda. So basically what we're trying to do is we're trying to go from counting in guests, right, over to counting in soda. Now, you may have already figured it out. I want you to actually pause the video here and try to work it out on your own, right? So I'm going to give it a couple of seconds. And all right, we're back. So hopefully you paused it, you tried to figure it out, and what you can see is that in this example is kind of simple. All you need to do is multiply the number of ounces of soda for each guest times the number of guests. So if we do our 15 guests that we need, right, and we multiply that 15 guests times, right, 12 ounces of soda, right, divided by, because again, each guest will drink. That's like saying each guest, right, one guest per 12 ounces. And we said before that per means what? Per means division. So each guest will drink 12 ounces. We can say 12 ounces of soda. Per means division. Per one guest, right? And when we do that, what we end up with, right, we end up with what we end up with is we end up with a situation where we can just multiply. Now, what we'll see here is that because the guess on this side is in the top, right? The 15 guess, that guess is in the top, and this guess is in the bottom. They will cancel each other out. And so we just have 15 times 12. All right, 15 times 12 is what? 15 times 10 is 150, and 2 times 15 is 30, so 180. So what we'll end up with is that we need 180 ounces of soda. Now, what you probably did is you probably just did 15 times 12. And that's okay for right now, but we're going to go into this way that I did it, right? So 15 times 12 equals 180. You probably got your answer, 180 ounces of soda, just like that. And that's perfectly fine. But what we want to develop is kind of a systematic way to do it, right? So if we had a more complicated example, we would need a systematic way of doing it so that every time we can ensure that we get the correct answer every single time. And so we're going to move on and talk about is conversion factors. And conversion factors are basically what allow us to do that systematic method. So basically a conversion factor is what we call an equivalency, meaning the two things are not exactly the same, but they have the same value. So they're not the same, right? But they have the same value. So in our previous example, what do we have? Our equivalency was that one guest, when we're at the store and we're buying our soda, is equal to what? One guest is equal to 12 ounces. Right? That's our equivalency. One guest equals 12 ounces. No, we're not saying that one guest is the exact same thing as 12 ounces of soda. What we're saying is that when we're at the store, for every guest that we have, we can swap them with 12 ounces of soda. For all intents and purposes, 12 ounces of soda is the same or equivalent, has the same value as one guest, right? And what that equivalency lets us do is it lets us convert from one unit to another unit. So just like what we were trying to do a second ago, where we were trying to count the number of people we would have at our party in ounces, right? We were trying to count it in ounces instead of counting it in guests, right? That's what a conversion factor allows us to do. And sometimes, right, we'll get the conversion factor in the problem statement, right? So just like in that previous example, we got the conversion factor from the problem statement, just like then, right? We had the problem told us that one guest is going to drink 12 ounces. We can also sometimes make up our own conversion factors. So people do that all the time with money, where it's not like a fixed thing, but it's just based on the markets and stuff. So the number of euros that equal how many dollars, where it's a conversion factor and equivalency, right? Sometimes we'll get the conversion factor just from like science. So an example of that might be 1 foot equals 12 inches. Right? 1 foot equals 12 inches, where basically that's an equivalency between feet and inches. Let's move on. So here's an example. Right? Let's say our problem statement said that one table holds 5 students. That is the same as saying one table is equivalent to 5 students. Now, you can see how we wrote it down here. One table, right? And then the division line, 5 students. So one table, we can say, whenever we see a division line, what can we say? We can say per. So one table per 5 students. Or we could say the opposite. We could say 5 students per one table. Right? And when we write it like this gives us a clue as to why we call it a factor. Because we're actually going to end up multiplying by this thing here. for either one, the one table per 5 students or the 5 students per one table. And basically what this tells us is that anytime we see 5 students, we can replace it with one table, or vice versa. Right? We can do the opposite, where anytime we see one table, we can replace it with 5 students. Let's do an example really quickly. I'm going to make up a problem, and I want you to pause it, try to solve it, and then come back. Right? And then I'm going to explain to you what I find to be the best method. So let's use our one table, 5 students example. So let's say we have a classroom. So I'm going to write up the whole problem. So we have a large class. Right? Just like our class. We have a large class of 57 students. We have a large class of 57 students. And we want to find out how many tables we need for how many tables we need to accommodate those 57 students. We need for the entire class. So we want to find out how many tables we need for the entire class. So just like the previous problem, we know that one table can hold 5 students. Right? We know that one table can hold 5 students. How many tables do we need? How many tables do we need? Now, again, the best way to approach all of these problems, just like any problems we've seen before, right, is to approach it using our find given solution. So first, what are we trying to find? We need to find the number of tables. Right? That's what we need to find, the number of tables. What's the problem giving us? The problem is giving us 2 things. So let's do our given. The first thing the problem gave us is how many students we have. So it's 57 students. That's how many students we have. Now the problem gave us another thing. The other thing the problem gave us is it gave us a conversion factor or an equivalency, right? And the equivalency was what? One table is equivalent to 5 students, right? That's the equivalency factor that the problem gave us. Now, the last thing I want you to do when you're given, right, when we're doing unit analysis, is I want you to make a plan. The way we're going to make our plan is we're going to say, what kind of unit are we starting with? So what unit are we starting with? We are starting with students, right? That's what we're starting with. We're starting with the unit that is students. So what we're going to say is we're starting with students. You don't need to write any numbers here. We're just drawing arrows. So we start with students. And what unit do we want to end up with? Well, it's in our find, right? We want to end up with what? Tables. So we start with students and we want to end up with tables. Now, the reason why we want to write this, right, is because the number of arrows that we draw when we do that plan, right, the number of arrows that we draw is the number of conversion factors we need. So the number of arrows we draw is the number of conversion factors we need. Conversion factors needed. So how many arrows did we draw? We only drew 1 arrow. So because we drew 1 arrow there, we only need how many conversion factors? We only need one conversion factor, right? Now, I'm going to say pause. So the next step that we need to do is we need to do the solution. I'm going to say pause it here. And I want you to try to find out how many tables we need to accommodate these 57 students, right? And then you can come back, play the video, and see if you did it the same way that I did it. All right, so we're back now. And what we're going to do is we're going to start off our solution. I'm going to show you a method. Now, I want you to just kind of watch. It may look like it's a little different than what you're doing, but it's probably not as different as you think. So what we're going to start off with is we're going to write over here the unit that we start with. What unit do we start with? We started with 57 students. So we're going to write that down. Now, the last thing that we're going to do is, not the last thing, the next thing that we're going to do is we're going to write the unit that we want to end up with. We're going to give some space. So we're going to write it over here. We want to end up with a number of tables. Then I'm going to draw a line going under them. Now, I'm going to look up here. How many conversion factors do we need? We only needed one because we could go directly from students to tables. There might be some cases where you need like an intermediary conversion factor where you need more than one. But in this case, we only need one. So what I'm going to do is I'm going to draw a line here. And I'm going to draw a line here. And this space here, let me highlight it so you can see what I'm talking about. I'll use this one. This space here, right, is where we are going to write our conversion factor. Because we only needed one, we only need one space. Now, when we look at it, what we want to do is we don't want this students unit in our answer, right? We don't want students in our answer. What do we want? We want tables in our answer. So we need to figure out a way to get rid of that students unit. So what we're going to do is we're going to try to put the students unit in our conversion factor. Here's our conversion factor. We're going to put the students unit in the bottom, right? So that way the students can cancel out with the students that's in the top. So that's what I'm going to do. I'm going to put 5 students. That's in the bottom. And I need to put the other part in the top. 1 table. And I want the students to cancel. That's why I put the students in the bottom, right? If I started off with the students in the bottom, then I would need to put the students in the top to make it cancel. And we'll do an example like that too. So when we do this, right, each of these lines is multiplication. Now this last line, because there's nothing else there, is going to be our equal. The last line is always your equals. So the first line is multiplication, the last line is equals. And what we're going to do here is we're going to cancel. So this students cancels with this students. And look at that. What unit are we left with? We are left with you can't really see that. We are left with tables. That's the unit that we're left with. So now what we're going to do is we're going to multiply. Now, each of these, treat them all like fractions. This is like a fraction bar. The line in the middle is a fraction bar. Right, so each of these are fractions and we need to multiply. So there's no number in the denominator here, so we're just going to put 1 down here. And how do you multiply fractions? You multiply across the numerator, you multiply across the denominator. So I'm going to do 57 times 1. And when I do 57 times 1, what do I get? I just get 57. And I'm going to do 1 times 5 in the bottom. What do I get? 5. And now this here is our answer. I mean, obviously, we can do more than that. We can actually divide it to get a number that we can kind of make sense of. So I'm going to say equals, and let's do 57 divided by 5. I'm going to pull out my calculator so I can give you the exact answer with the decimal. So 57 divided by 5, I get what? 11.4. So we get 11.4 tables. And because you can't have half a table, we're just going to round that up we need 12 tables. Our last table just won't be completely full. So we need 12 tables. Now, some takeaways. This method that I just did, we're going to do some more examples of it. But this method that I just did here, this is like what I think is the best method to do unit conversions. This is the best method to do unit conversions, right? And it's a very useful method, and it's kind of simple. It may look complicated at first because this seems like a really simple example, but when you do complicated examples, this method allows you to kind of keep track of everything that you're doing. So we're gonna do another example. So hold on. Okay, so I had a little technical difficulty there, but that's why this problem just appeared. But let's do another example. So in this example, we're buying land, right? And the land costs $16,000 per acre. Right? That's the cost of the land, $16,000 per acre. Now, we want to know how much would 62 acres of land cost. Right? So that's what we're trying to buy. 62 acres, we want to know how much it'll cost. So what I want you to do is I want you to pause the video here, and I want you to try to solve it on your own. Try to do the method that we just did. And when you're ready to come back, just unpause the video and play it to see how I solved it. So I'll just give you a second to pause it. All right, and we're back. So again, what do we need to start with? We always start with the find. Always. Don't be lazy, start with the find. So what are we trying to find? We are trying to find the total cost, right? That's what we're trying to find. And then when we write the find, particularly when we're doing unit analysis, we need to write what unit we want to end up with. And in this case, we want to end up with a dollar amount, right? Where we can't go to the bank and say, oh, I'm trying to buy 62 acres of land. We need to go to the bank and say how much money we need. So we need the value of the land in dollars, right? So the 62 acres is telling us one measurement of the land, but we need to measure that land in a different way. We need to measure that land in dollars. So now we can go to the given. And the problem is giving us a couple of things. First, what are we starting with? We're starting with 62 acres, so we're going to write that down. We start off with 62 acres. The problem is also giving us a conversion factor or an equivalency. What's the equivalency? $16,000 per acre. So we can write that. That means every acre costs $16,000. So we're going to write that. $16,000 equals 1 acre. Right? That's our conversion factor or our equivalency. And then the last thing is we need to always make a plan. So when we make our plan, what are we going to do? We're going to say we're starting with acres and we want to go over to what? Dollars. Right? We're trying to turn our acres into dollars. We want to count the land in dollars again, right? Because that's what we need when we go to the bank. So now let's do our solution. So the first thing we're going to do, we're going to write what we're starting with. We're starting off with 62 acres. And we're going to give some space, and we're going to write what we want to end up with. We want to end up with dollars. And then we're going to draw one line all the way across. Now, how many conversion factors do we need? We only need one because in our plan, we only drew one arrow. And we're going to draw space. Leave a little extra space. We'll draw space, right, for that conversion factor. Now, here's the question. Do we put the $16,000 in the bottom, or do we put the 1 acre in the bottom? Well, we can look at it. What do we want to cancel and what do we want to end up with? if we want to cancel acres, see we have acres here, we want to cancel that. That's not in our answer. Here's our answer. We want an answer in what? Dollars. So because we want to cancel acres, we need to put acres in the bottom. So we put the acres part of our equivalency in the bottom. So we're going to write 1 acre. That way it can cancel out. And our answer needs to be in dollars, so we want the dollars in the top. See, in our answer, the dollars are in the top. So that means in our conversion factor, we also want the dollars to be in the top. So we're going to write out $16,000 in the top. Now here, what cancels? Our acres cancels with our acres, so they cancel. And what are we left with? We are only left with dollars. And isn't that what we wanted? We want it to be left with dollars. So now it's time to pull out your calculators and multiply. So we're going to do 62 times 16,000. So we do 62 times 16,000. And what I end up with is $992,000. I just multiplied. I multiplied across the top, and then I'm going to multiply across the bottom. So there was nothing under the 62. So I'm just going to put a 1 down there, and we did 1 times 1. We get 1. Again, multiply across the top, multiply across the bottom. So our final answer is what? $992,000. That's our final answer, $992,000. Right? So when we do it like this, it stops us from making mistakes. Right? It stops us from making mistakes because we have a clear, systematic way of approaching the problem. Right? The next thing, let's do another example really quickly. Let's do another example. So I'm going to draw a line all the way across. And I'll even write it in a different, not write our next example in a different color. So the next example that we can do, let's say we need a medication, right? So a doctor orders, let's say a doctor orders 96 grams of medication for a patient, right? For a patient. So if let's say each pill contains, let's say each pill contains 0.08 grams of medication. Each pill contains 0.08 grams of medication. Okay. The question is, how many pills will the patient need? That's the question. How many pills will the patient need? So go ahead, pause the video, right? And then come back to it in a second. Try to solve it. Try to do it in this method. Try to do it this way that I'm showing you, and then come back to it, right? So let's go ahead and try to solve it. So, well, I'll give you a second. Pause the video and come back. All right, so now we're back. We'll start with a find. What are we trying to find? We are trying to find a number of pills. How many pills will the patient need? So find number of pills, right? That's what we need to find, a number of pills, right? And our given problem is giving us a couple of things. First is telling us what we're starting with. What are we starting with? We're starting with 96 grams of medication. So we start off with 96 grams. The problem also gives us a conversion factor. What's our conversion factor? Each pill contains 0.08 grams. So 1 pill equals or is equivalent to 0.08 gram. So 1 pill equals 0.08 grams. And then lastly, we need to make a plan. So what's our plan going to be? We're going to start off with what? Are we starting off with pills? No. We're starting off with an amount of grams. Let's imagine we're the pharmacist and we're making the medication. So we're starting off with the number of grams. And what do we need to end up with? A number of pills. So we have grams in the beginning and we need to end up with a number of pills. So let's do our solution. So in our solution, what do we need to do? First, we write what we're starting with. We're starting with 96 grams. We give some space and then we write what we want to end up with. We want to end up with a number of pills. How many conversion factors do we need? We only drew one arrow in our plan, so we only need one conversion factor. So we're going to draw a line underneath. Since we only need one conversion factor, we're going to make space for one conversion factor. That's the space here. And we're going to write in our conversion factor. So let's look at our equivalency. We see that 1 pill equals 0.08 grams. Now, what do we want to get rid of? We want to get rid of the grams. So where should the grams go? Take a second and think about it. Should we put grams in the top or should we put grams in the bottom? So since we want to get rid of it, grams is already in the top. The way we cancel it is by putting grams in the bottom. So that's what we're going to do. We're going to put a grams part in the bottom. We're going to put 0.08 grams in the bottom. And in the top, we're going to write 1 pill. Now, our grams can cancel. And what do we be left with? We'll be left with pills. Now we can multiply across the top. 96 times 1 is 96. Now we multiply across the bottom. There's nothing under the 96, so we're going to put a 1 under there. 1 times 0.08 is... How did I get blue? How did I turn blue? Sorry about that. I'm going to go back to red. 1 times 0.08 is 0.08. Notice I didn't write the grams because the grams is not there anymore. Canceled. Now I need to do some division. So I'm going to do 96 divided by 0.08. So 96, pull out your calculators. 96 divided by 0.08. And we end up with 12,000 pills. Right, so that's a lot of pills. This patient's going to be taking pills for a long time. So 96 divided by 0.08 was 12,000. It's a lot of pills. Right. Now, so that example was kind of straightforward as well. What you may have done, if you just did it by yourself without doing it this method that I'm showing you, is what a lot of people will do is they'll do 96 times 0.08 just because they think that's what you're supposed to do. And what you'll see is if you just did 96 times 0.08, one, you would have done it wrong because what do we need to do? We need to do 96 divided by 0.08. But if you did 96 times 0.08, you would have gotten 7.68 pills. Isn't there a big difference between 12,000 pills, 1,200 pills, and 7.68 pills? There's a big difference there, right? Which is why math is important. Because if you were a pharmacist and you hadn't paid attention in math class, you might have made that mistake, and then you would have been severely under giving a patient their medicine, right? So we don't want to just assume the operation. Write it all the way out. Do the box method. Do the grid method. Right, so that you can get the accurate answer. So let's do another example. So this example we're going to do is going to actually be a little more complicated. Right? So what we're going to do is, let's say, how many feet per second is 95 miles per hour. So seems like a simple question, right? But that's the question. How many feet per second, right, is 95 miles per hour? So basically, we're measuring now in miles per hour. And what do we want to measure in? Instead, we want to measure in feet per second. A practical application might be, let's say you were like a highway patrolman or something, and you were trying to explain to somebody how fast they were traveling. So how many feet they would travel in 1 second if they were actually going 95 miles per hour. Right? So like an example might be, let's say you were going 95 miles per hour and you look down at your phone for 5 seconds. If you look down at your phone for 5 seconds, how far would you travel in those 5 seconds? Right? How many feet would you travel in those 5 seconds? So let's do it. So our find is pretty straightforward. Find is simply feet, right, per second. That's what we're going to do. We just want to find how many feet per second we end up with. Our given might not be so simple. So for our given, right, the first thing we know is we're starting with 95 miles. Now again, this keyword per means what? Division. 95 miles. Let's write it differently. 95. This is what we're starting with. 95 miles per hour. Right? 95 miles per hour. Right? Again, per means division. So there goes what we're starting with. Now, in this case, we have a couple of equivalencies, but the problem doesn't tell us any equivalency. So in this case, it would be kind of up to you. I know a lot of people don't know how many feet are in a mile, for example, so I probably would tell you this if it was a test or something. But in most cases, you could just Google it. So I'm going to Google it right now. Okay, Google. How many feet are in 1 mile? Let's try that one more time. How many feet are in 1 mile?
1 mile is equal to 5,280 feet.
Okay, so that's our first conversion. Now notice, we have 2 units in our initial thing. We have miles, right? We have miles, and we also have hours. One is measuring distance and one is measuring time. So we need equivalencies for both of those, right? So starting off, Google just gave us the equivalency for the distance, and they said 1 mile is equivalent to 5,280 feet. Now, what about hours to seconds? Right? Well, for hours to seconds, I don't know about you, but I can't go straight from hours to seconds. But what I do know, I know that 1 hour is equal to what? 60 minutes. But I can't stop at minutes, can I? Because I need to get what? I need seconds. So I'm going to do it again. 1 minute is equal to what? 60 seconds. Right? So now I have 3 things. I'm sorry. I have miles to feet. I have hours to minutes. And I have minutes to seconds. Right? And if we look at it, that's what I need to do. I need to turn my miles into what? feet. And I need to turn my hours into what? Seconds. Right? So now let's make our plan. So we won't be able to do all of these at one time, but we can do them step by step. In step one, right, the first part of this process will be, let's start with turning our miles into feet. So we'll do miles into feet. We'll be partway there. Then we need to do what? Hours, and turn them into minutes. Then we need to do minutes and turn them into what? Seconds. So here's our plan. And now notice here, how many arrows did we draw when we made our plan? We drew 3 arrows. So how many conversion factors will we need? We'll need 3 conversion factors. All right, so when we do the solution, now at this point, I gave you a big hint. And I want you to pause the video here. And I want you to try to complete the rest by yourself. All right, so I'm about to start back up. Actually pause the video. Don't just watch it, because if you just watch it and don't try it yourself, you won't understand it. So I want you to actually pause the video and try to solve it yourself. So when we do the solution, all right, let's start it. So go ahead and unpause it to see if you got it correct. We're going to start by writing what we start with. What are we starting with? We are starting with 95 miles per hour. Now, hour is just like 1 hour. So we're going to write 1 hour. That's what we're starting with. 95 miles per 1 hour. And what do I want to end up with? I'm going to write it all the way over here because I need 3 spaces. I'm going to write it all the way over here. We need to end up with feet per what? Second. So we're starting with miles per hour. And we want to end up with feet per second. So I'm going to draw my line. Step 2, draw my line all the way over. I'm going to connect both of my fraction bars. And now how many spaces I need? I need 1, 2, 3 spaces. So that's what I'm going to make. So here's 1 space, 2 spaces, 3 spaces. Let me actually make these spaces a little smaller. So that's 1 space, 2 spaces, 3 spaces. Now I'm going to do each of my phases. Right? Each of my conversions is going to happen inside of one of these spaces. That'll be the first one. This will be the second one. So the first one I'm going to do from miles to feet. Second one I'm going to do from hours to minutes. And the third one I'm going to do from minutes to seconds. Now I want you to note something. What I'm about to do is I'm just going to write all of my units out. I'm not actually going to do any numbers yet, right? I'm still kind of mapping my path out. A lot of times people make a mistake because they'll start working with the numbers too fast. We don't want to work with the numbers too fast. We want to start off with just working with the units and manipulating the units first. So the first part of my plan is to do what? Miles to feet. So I want to get rid of this miles, and I want to end up with feet. So I know I want to get rid of the miles. Miles is in the top in the first one, so where do I need to put it? Yes, I need to put it in the bottom. I need to put miles in the bottom. So which conversion factor I'm going to use? I'm going to use this first one up here. And I'm going to put 1 mile in the bottom. And I put the other part, 5,280 feet in the top. Now, when I do this, what's going to cancel? Miles is going to cancel with miles. What I'll be left with feet. Now, what do I have? I have feet in the top, and I have hour in the bottom. So this is feet per hour, because again, remember, division means per. Per means division, division means per. So I have feet in the top, hour in the bottom. So let's continue. We're not done yet because we want feet in the top and seconds in the bottom. Now I have hour in the bottom here, and I want to get rid of it. My second conversion factor, right, has hour in it, doesn't it? 1 hour equals 60 minutes. Now, where do I want to put the hour? I want to get rid of it. Right now, I have hour in the bottom here. Where do I need to put the hour to get rid of it? Well, it's in the bottom. To cancel it, I need to put it in the top. So I'm going to put it in the top. 1 hour equals what? 60 minutes. And there we go. Now, what's going to cancel? My hour here, right? Uh-oh. That's not what I wanted to do. How do I undo that? Let's just erase it. Okay, there we go. My hour here is going to cancel with my hour here. And now what do I have? I have minute in the bottom. I have feet in the top. So now I'm at feet per minute. Now for the next one, I'm not done yet because I want what? I want feet per second, not feet per minute. So now I need to cancel my minutes out. Now to cancel my minutes out, what do I need to do? Well, I'm going to have, where do I need to put it? Well, I'm going to use this one down here, the last one. 1 minute equals 60 seconds. And my minute is in the bottom, so I need to put my minute where? Yes, in the top, because I want it to cancel. So 1 minute in the top, 60 seconds in the bottom. And now I can cancel it. Minutes cancels with minutes. And now what am I left with? Seconds. Now let's just do a check. Now we want to check and make sure that the only units that we have left, we didn't do this before because the other examples we did were kind of straightforward. But this is what you want to do whenever you had a problem, really. You want to check and make sure that the units you have left are the units you want. What's the only unit left in the top that's not canceled out? Well, there's an arrow next to it. Right? What's the only unit that's not canceled out? The only unit that's not canceled out in the top is feet. And the only unit that's not canceled out on the bottom is seconds. And isn't that what we want? We want feet per second. So our check made sense. Now we multiply across the top, multiply across the bottom to get our answer. So let's multiply across the top. We have 95 times 5,280 times 1 times 1. 95 times 5,280 times 1 times 1. And we end up with 501,600. So 501,600 in the top. And in the bottom, we have 1 times 60 times 60. 1 times 1 times 60 times 60. And we get 3,600 in the bottom. Now we can do some division. 501,600 divided by 3,600. And I end up with a whopping, I end up with 139.33 feet per second. So that means if you are traveling 95 miles per hour, every second you travel 140 feet almost. 140 feet in 1 second, right? That is almost half a football field. Right? That's almost half a football field in 1 second. So if you look down at your phone for, say, 6 seconds, you're traveling like 3 football fields in those 6 seconds if you're driving 95 miles per hour. So that's my PSA. Don't text and Thank you for coming to my TED Talk. So don't text and drive. Right? So you can go back over this example here again if you want to, but you'll see more examples like this where you have multiple different units to work with. Right? And again, by doing this box method, it's very systematic. At each step, you say, what am I trying to convert? Okay, I know what I want to end up with in the next step, right? Let me get the right equivalency or conversion factor. And that's all you need to do. All right, moving on. So in life, right, a lot of times we have what we call standard units, right? We have standard units. So standard units make things more convenient because they're basically measurements that we all agree on. So if you've ever measured something like with your feet, where you just walk with one foot in front of the other, imagine if everyone measured stuff like that. Then when somebody said this thing was 9 feet, 9 feet for me might be different than 9 feet for one of you all if your feet are smaller than mine, right? So instead, we have a standard unit of measurement where we have what 1 foot looks like, and it's 12 inches, right? In the United States, we use what's called customary units, right? And everywhere else in the world, they use SI units or scientific units or international system of units is what the SI stands for. Right? The SI units make a whole lot more sense, and you'll see it. And basically, the only people that use customary units are just us in the United States. Because even in the United States, if you're doing science or engineering or anything, you do customary units. And basically, there are a couple of things that we want to measure. Particularly, we want to measure mass, or like how much stuff there is. We want to measure time, temperature, distance. I already said temperature. I don't know why I wrote it twice. I'm going to cross that out. Right. Time, temperature, distance, and mass. Those are like the basic things to measure. So we'll start off with temperature because that's kind of the easiest. So there are 3 ways that we can measure temperature. I put an asterisk there because there's a 4th way that almost no one uses. The first way we use is Fahrenheit. I think that's what we're all used to. Then there's Celsius, and then there is Kelvin, and we can convert between all 3. So if we want to convert from Fahrenheit, right, to Celsius, or well, we're actually starting from Celsius to Fahrenheit. We'll do some examples in a second. So if we want to convert from Celsius to Fahrenheit, then what we need to do is we need to multiply by 1.8 and then add 32. So the actual formula looks like this. The Fahrenheit measurement equals 1.8 times the Celsius measurement plus 32. And if we want to go from Fahrenheit to Celsius instead, we need to subtract 32, then divide by 1.8. So we do the Fahrenheit measurement minus 32 divided by 1.8, and that's the formula. Now, Kelvin, right, is like what we call an absolute scale, right? So there's no negative numbers in Kelvin. So like the same way we can have -3 or -5 or -10 degrees, you don't have negative numbers in the Kelvin scale, right? So if we want to convert from Celsius to Kelvin, we just add 273.15. Here is the formula. We just add 273.15. And to go from Kelvin to Celsius, we subtract 273.15. So if we want to go from Fahrenheit to Kelvin, what we need to do is we need to convert to Celsius first and then go from Celsius to Kelvin. So let's do an example real quick. Let's say we want to go from 55 degrees Fahrenheit to Celsius, for example. Well, we're going from Fahrenheit to Celsius, so we need to write the formula. Fahrenheit to Celsius, C equals F minus 32 divided by 1.8, which equals 55, because that's F. F is the Fahrenheit temperature. So we have 55 minus 32 divided by 1.8. 55 minus 32 is what? 23. divided by 1.8. I'm going to do that last part in my calculator. So we have 23 divided by 1.8, and we get 55 degrees Celsius is 12.78. 55 degrees Fahrenheit, I'm sorry, is 12.78 degrees Celsius. Right, that's what we get. Now, let's say we're doing another one. That'll be our first example. Let's say we were going from, let's say, 20. Let's say we're doing 29 degrees Celsius to Fahrenheit. Right? Well, we write the Fahrenheit formula. F equals 1.8 times the Celsius measurement plus 32. And that's 1.8 times, what's the Celsius measurement? We said 29 degrees Celsius. So 1.8 times 29 plus 32, which equals, do this in my calculator, 1.8 times 29 is 52.2 plus 32 equals what? 84.2 degrees Fahrenheit. So there's an example. We're going from Celsius to Fahrenheit. And then let's do an example from Fahrenheit, from Celsius to Kelvin. So let's say we had 80 degrees Celsius. We're trying to convert it to Kelvin. We just take our Celsius measurement, right? Kelvin equals Celsius plus 273.15. So we have 80 plus 273.15. We end up with 80 plus 273.15, and we get 353.15 degrees Kelvin. So those are 3 different examples. You can just pick random temperatures and convert them. I think that's probably the easiest way to do that. Do some practice problems. Here we have the actual scale. So we can see that we have different absolute 0 points. So absolute 0, we can't get colder than it, is 0 Kelvin, or minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. And then water boils at 100 degrees Celsius, freezes at 0 degrees Celsius, boils at 212 Fahrenheit, freezes at 32 degrees Fahrenheit, and boils at 373.15 degrees Kelvin, freezes at 273.15 degrees Kelvin. Moving on, here are some of the U.S. customary units, right? And like some of the equivalencies. If you look in the back of your book, like if you look in the back of your composition notebook, you'll see a bunch of little things. You can also Google these to get them. But basically, it's just saying these things are equivalent. So, for example, 1 pound is equivalent to 16 ounces. Just like that. 1 pound is equivalent to 16 ounces. Here are a bunch of time measurements. These ones are very useful. You should know these, right? 1 year is 52 weeks. You should know all of these things. So you should know these. Like, by know them, I mean know them by heart. You should know that, you should know that 1 cup is 8 ounces. You should know that 1 foot is 12 inches. You should know that 1 yard is 3 feet. Those are the ones I'll say that you should definitely know, right? You should just know all of these. There's no excuse for not knowing any of these. You should know all of these ones. on. We have SI units, right? Now, SI units are a little different because in SI units, instead of scaling in like random ways and we get to the next biggest unit by just doing like some random calculation, like 1 foot equals 12 inches. That's kind of random, right? Instead, we have what's called base units, and we scale in a different way. So the base units in SI, in the SI system, right? The base units are meter, gram, right? Second. And those are the ones that I'll kind of stick to. These other ones are base units, and you'll see them, but those are the ones we're primarily going to work with: meters, grams, and seconds, right? And what you need to know here is that each of these units has a symbol associated with it, right? So each unit has a symbol associated with it. So instead of seeing meter, you may see M for meter. And when you see that little M, it represents meter. Now, meters measures length. When you see a G, in particular a G, because the K means kilo. That's what the K means. The G means gram. So when you see that, that means gram. When you see S, it means second, right? Grams measure mass, or like how much stuff there is. And seconds measure time. That's what seconds measure. They measure time, right? So moving on again, these are just kind of like the basic units. Don't forget, each of the units has a symbol associated with it. That is important as well. Now, the way we scale SI units is with what we call prefixes, right? We call them prefixes. Now, to scale them, right, basically, we put a prefix on the end, and the prefix is like a counting thing. So an example, let's say you were talking to your friend, and you were trying to tell your friend that you just found $20,000. Are you going to text your friend and say 20 and write it all the way out? Or are you just going to be like, I found 20K, right? Where the K means what? The K means 1,000. And that's all the prefixes are. They're just like numbers. So how K means 1,000 there, we can say 20K or 20,000, right? All the SI unit prefixes that I'm about to show you are just numbers in that way. And K, the reason why we say K for 1,000 is actually because K means kilo, right? And kilo means we have 1,000 of the unit instead of just one. So if we have 1 kilometer, we're saying we have 1,000 meters. Right? Now, an important thing is that when we are scaling units in the SI system, right, we use multiples of 10. That's how we scale the units, using multiples of 10. So to get to the next biggest one, we multiply by 10, and that gives us the next biggest unit. And each of the multiples of 10 that we use has a different name. So if we were to multiply by 10 3 times, 10 times 10 times 10 is 1,000. The name for that would be kilo. That's the name for that. Now, an important note. Well, actually, let's do that on the. So if we look here, here are all of the different prefixes that we can have. So if we have deci, that's a D. D is the abbreviation for it, and that means 1/10. Centi is a C, and that means 1/100th, right? Now, for these ones, if you look at it closely, you can see that deci is 10 to the minus 1. Centi is 10 to the minus 2. Excuse me. Milli is 10 to the minus 3. Micro, notice it skipped from milli to micro. It skipped to minus 6, 10 to the minus 6. Nano is 10 to the minus 9. And pico is 10 to the minus 12. Basically, If we see centi, we're saying divide by 10 2 times, because centi is 10 to the minus 2. If we see nano, we're saying divide by 10 9 times, because nano is 10 to the minus 9. So each of those negative exponents is telling us to divide by the number that many times instead of multiply by that many times. So we have these different units, and that's what each of the different units means. Each of the different prefixes means. Getting stray markings here. And you need to know these abbreviations. So that's the smaller ones, right? That's the smaller ones. And then we have larger ones that you're used to. The one you've probably seen is kilo. Right? We've all seen kilo. And kilo means what? 10 cubed, which is 1,000. We also have deca, which is 10 to the 1, which is 10. We have hecto, which is 10 to the 2, which is 100. We have kilo, we already said that, that's 1,000. The K is 1,000. We have mega, which is a big M. Note, it's a big M, not a little m. Big M for mega, not a little m. We have giga, which is 10 to the 9th, which is a billion. We have tera, which is 10 to the 12th, which is a trillion. Right? Now, these larger ones are multiplying by 10 a bunch of different times. That's what the larger ones are. We're multiplying by 10 a bunch of different times. Now, when we do these, there are a couple that you need to memorize. The ones you need to memorize the highlighted ones. So you need to know centi. That means you need to know the word centi, the prefix, and the value. You need to know milli, the prefix, the abbreviation, and the value. Micro, nano. You also need to know kilo, mega, and giga. Right? You need to know those ones. Those are like the common ones that you'll see. Right? Now, one thing to note, let's say we were trying to write out a unit. Right? How do we write it? How do we write the prefix along with the unit? Well, it's a prefix. Prefix means it comes first. So let's say we were trying to write centimeter. Right? So let's say we were trying to write centimeter. How do we write that in an abbreviated form? So for the centi is what? A C. So we write a C. Meter is what? An M. So we write an M. So if you go back and look at the SI units one, you'll see that meter is an M. Now this is important. The way we write this is important because whenever you see two letters and we're dealing with SI units, the first letter is always going to be the prefix. And the second letter will always represent the unit. Now, what if we didn't have two letters? Let's say we just had one letter. If you just see an M and we're dealing with SI units, what does the M mean? Well, in this case, we can say that there is no prefix, right? When we just have one letter, this M, it's a little m, it doesn't mean milli, right? There's no prefix on there. Or it would be 10 to the 0 would be the prefix. 10 to the 0 is what? 1. So there's no prefix there. So that M is just the unit. It just means meter. When we have one letter, it's just the unit. There's no prefix. Right? And that's important just so you don't get confused. If you just see one letter, it's just the unit, not the prefix. And if you see two letters, the first letter is the prefix, the second letter is the unit. Now, one other note. See this micro here? When you see micro? See micro? That symbol there is a mu. Right? That's what that symbol is. And that's what we use for micro. We don't really use the MC. We mainly use mu. And that's mu right there. That's what mu is. Right? That little symbol there. And it looks like this. This is how you'll see me write it. I think it's MU. Mu. That's what it means for micro. So just a little note on the side if you see that and you're like, what does that mean? So that's prefixes. And again, remember, 2 units, 2 letters. The first letter is the unit. The first letter is the prefix. I'm sorry, I'm getting myself tongue-tied. The first letter is the prefix. The second letter is the unit. 1 letter by itself, it is just the unit and there is no prefix. Now, one thing that we sometimes have to do, sometimes we have to convert from one SI unit to another SI unit, right? And it basically saying we want to write it in a different way. So you know how everybody will say, oh, I'm going to run a 5K? When you run a 5K, what you're actually running is 5 kilometers. So let's say we didn't want to write out 5K, we didn't want to write 5K as kilometers. Let's say we wanted to write our 5 kilometers instead as centimeters. Well, what would we need to do? We would need to convert this into this. And how do we do that? Well, there's a very simple way to do that. It just requires a little bit of counting. That is all it requires. That's it. Nothing else but some counting. So the first thing we need to do, right, is we need to write our number. And if there is no decimal point, we're going to write the number by itself with 0.0. So similar to how we did scientific notation, we're going to start off by writing 0.0. Now, the second thing we need to do is we need to draw a little number line. We're going to draw a number line. Now, this is a special number line. This is what I call a reverse number line. So in the middle of our number line, we're going to put 10 to the 0. Now, going to the left, normally we expect numbers to get bigger, but instead get smaller when we go to the left, but instead they're going to get bigger when we go to the left. So when we go this way, instead of going 10, like to the minus 1 or something, when we go this way, we're actually going to go here and say 10 to the first power. And then we're going to say 10 to the second power. And then 10 to the third power. I'm going to keep going. Now, remember, when we were at 3, we skipped to what? We skipped to 6. So I'm going to write 10 to the 6. But I don't want to make a mistake, so I'm going to put lines in the middle. So it's 3rd, 4th, 5th, and then 6th. Just so I don't make any mistakes here. I put little lines, but I know the next one is 10 to the 6th. Sorry about that. It's a bit of technical difficulty. Okay, so I put 10 to the 6th there. Now going in the opposite direction, clean this up really quickly. Going in the opposite direction, we're going to go another way. We're going to say 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. Okay, yeah, that's my technical difficulty there. It keeps just drawing random stuff. Bear with me. Hold on. Okay. I'm going to keep going. Remember when we were at minus 3, what did we skip to? 10 to the minus 6. So we need to put 5 and 6 there. And then we I'll do one more. 10 to the minus 9. Now, to do the conversion, right, and if we're doing a bunch of problems, we only need to draw this once. To do conversion, we look at what we start with and where we're trying to end up. So what are we starting with? We're starting with kilo. That's the prefix that we're starting with. Remember, we need to memorize these. So the K means kilo. So kilo was what? If we go back to our chart, right? If we go back to our chart, the kilo is here. That's K. K was 10 to the third, 10 cubed. And where are we trying to go? We're trying to go to the C. The C is what? Centi. That's minus 2. So we're trying to go from the K to the minus 2. So we're going to do similar to what we did with the scientific notation. We're going to just count. So we're starting here. We're going to go 1, 2, 3, 4, 5. We moved over 5 spaces, so our decimal point needs to follow it and move over 5 spaces as well. 1, 2, 3, 4, 5. I'm going to add some zeros. And then we're going to rewrite our numbers so we can 500,000. 500,000, and then we write the new unit. Centimeters. And it is that simple. It's just some counting. Draw your reverse number line and then count. And that's kind of all there is to it. We're going to do another couple of examples. I'll show you what the reverse number line kind of looks like. Here's the reverse number line. Again, don't forget, you got to add. So this is kilo. Look at kilo. We can't just skip it. We got to go 4, 5, then we get to 6, 7, 8, then we get to 9, 10, 11, then we get to 12. And the same thing on the other side. When we have minus 3, don't forget, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, minus 10, minus 11, minus 12. So don't forget that. Don't forget to add those things in there. Let's do another example. So let's say we were trying to go from, let's say we had 20 centigrams, right? Grams is the unit, centi is the prefix. And we were trying to go to megagrams, right? So we start by writing out our 20. There's no decimal, so we put 0.0 at the end. We draw our little reverse number line. We have the 0 in the middle is 10 to the 0. And then on this side we have 1, 2, 3. It's 10 to the first, 10 to the second, 10 to the third. I'm being a little lazy. 4, 5, 6. And going the other way we have -1, -2, -3, -4, -5, -6. Now we're starting at what? What are we starting at? We're starting at centi, and we need to go to mega. Now another thing I like to do, you draw a little person. So we're starting at centi. Centi is what? If we go back to the chart, you'll see that centi is -2. Or the C, centi, is -2. So I'm going to draw a little person at the place that we're starting. We're starting here, draw a little person. Where are we going to? We look back at our chart, we'll see that mega, or big M, is to the 6th. So we're going from -2 to 6. So this is where we're trying to go to mega. This is centi. We're trying to go to mega. So I'm going to count. Let's do our little loops over. 1, 2, 3, 4, 5, 6, 7, 8. So I went 8 spaces over. So I need to go 8 spaces over in here in the same direction. 1, 2, 3, 4, 5, 6, 7, 8. I didn't leave myself enough space. Add a bunch of zeros, decimal point, and then rewrite it. So we have 0.10000020. That is our answer in megagrams. Let's do one last example. Let's say we were trying to go from kilowatts to gigawatts. So let's say we had 500 kilowatts. The K is the prefix. And we're trying to go to gigawatts. Here the G is the prefix. Right? So we write our number. 500. There's no decimal point, so we put 0.0. We draw a number line. Put the 0 in the middle. Now we're going from kilo to giga. So I'm not even going to write. I'll write one of them. -1, -2, -3. And on this side, we 1, 2, 3, 4, 5, 6. Giga is 9. So I definitely didn't leave myself enough space here. So I'm going to erase and make it a little longer. Because giga is 9, 7, 8, 9. There we go. Now we're going from kilo to giga. So kilo, right, is 3, 10 to the third. I'm gonna draw my little person here. Draw a little person. And I'm going over to what? Giga, which is 9. And I'm going to, I don't need to draw a person over there. I'll just jump over. 1, 2, 3, 4, 5, 6. Right, from kilo to giga. 1, 2, 3, 4, 5, 6. Count it over in the same direction. 1, 2, 3, 4, 5, 6. Decimal point 0, 0, 0. Then I can rewrite my number 0.000 500 gigawatts. Now I'm going to send you some problems. I want you to work through them. Try to solve them the best you can. I'll send you the answers as well. Again, when you do practice problems, make sure you don't try to look at the answers, because you got to do the problem without seeing the answer. Okay? And with that, we are done. Have a good night, everyone.